I'm going to tell you one that maybe isn't quite so familiar. Right, so the talk. Well, we had our direct experience of nature already. Then I'm going to tell you about color, then I'm going to tell you a little bit about the quantum theory of light. So color has always fascinated humans. Humans have been talking about it since the ancient Greeks, if not before. But it's also very useful to animals like us. You look around the world and you see this jumble of confusing sensations. You have to segment your visual world into objects, and luckily different objects have different colors. If you've got color vision, it really helps to segment the world into objects. And once you've done that, it really helps to figure out what they are, which is which. And in particular, at some point in our evolutionary history, it was really important for our ancestors to be able to distinguish ripe fruit from unripe fruit. You know, there you are up in the trees. It's going to save you a whole lot of time if you don't have to go over there, grab that fruit, stick it in your mouth, and see whether it's ripe or not. If you've got the right kind of color vision, you can just look at it and see. It's good for figuring out whether that person over there is the same species as you or not, and if not, just ignore them. It's good. Some animals use color for emotional signaling. Is that guy about to attack me or not? Or are you saying back off because I'm about to attack you? That can we use color for that. Okay, color, it's useful. I mean, color vision is useful, but not quite simple, right? We've made this uncomfortable observation that our eyes discard a lot of information about the spectrum of light. A lot of information comes into your eyes that doesn't make it into your brain, like the difference between those two kinds of yellow or those two kinds of white. So there's something we got to figure out. But you know, when there's something that doesn't fit, that's an intellectual opportunity. Doesn't fit our notions about our perfect eyes, maybe it's a chance to learn something. And the minute you get an intellectual opportunity, there's a technological opportunity that comes right after it. Maybe there's some way that I could view color that would not involve discarding that information. Could be useful. So here's some splotches of light. We know about that one. It's the whole spectrum. We know about that one as just one end of the spectrum, and that's the middle, and that's the other end of the spectrum. Then there's this one that could get split into just the red and the green. Here's one that we haven't talked about yet very much. It's magenta. You saw it on the screen a little while ago. Whoops. There we go. Come back. Yeah, okay. It's got the red, it's got the blue, and it has hardly got any green in the middle. It's red and blue without the green in the middle. That's the spectrum that causes magenta. And the cyan is something similar as well. Now I want you to keep those images in mind as we find another way of representing that. There's white light. I can put it through a prism. I get this smear of colors. There's equal amounts of everything. I want you to get used to thinking about this as a graph. Okay? On this axis, we've got where you are in the spectrum, which of those spectral colors we're talking about. And on this axis, we've got how much of that color is present. So white light has got a broad, flat top, about equal amounts of blue, green, and red. That's what we call white light. Whereas that magenta, it's got a lot of blue, it's got a lot of red, hardly any green. So we'll write that as a graph with bumps in it. There's a bump in the blue, there's a valley in between, and there's a bump in the red. Whenever you see these graphs in this talk, I want you to think about these smears of color that they're representing. So the hero of our story is a guy named Thomas Young. Fascinating character. You know, first he got a medical degree, but he never liked sick people, so he had to revolutionize science in a way that I'm going to tell you about tonight. But then he got sort of bored with physics as well and started translating the Rosetta Stone. One of those great guys that has a restless intellect. Let's stick with what he said about physics. He made a chain of reasoning that was incredibly modern for 1801. And I started out with things that he'd already learned from Isaac Newton. He said, well, okay, light comes in different flavors. I'm going to call those the spectral colors. Magenta is not one of them, right? I'm talking red, green, and blue. Even when you mix those colors, those kinds of light, those flavors retain their distinct character and can be separated once again. You just saw that, right? That was your direct experience. Other colors involve the relative amounts in the mixture of those flavors. That's what determines color. And our eyes must contain some mosaic of little pixels. Here they are, like in your cell phone camera. Each one of these is a living cell in the retina in the back of your eye. And each one of those has a line to the brain. That's how you represent a complex visual scene. Each one is measuring something about the light landing on it and telling the brain about it. And all the brain can possibly know about color is what it hears those cells saying. That's the modern thing. Incredible for 1801. Your brain can't tell anything. It's got no sensory organs of its own. All it knows is what's coming in the pipes. And what's coming in the pipes is information from these photoreceptor cells. Anything they can't tell, the brain can't tell either. And Young goes a little further. His key point, Every photoreceptor cell, he says, let's suppose it's only sensitive to a particular range of colors. The cells are tuned to particular colors. That's Young's big idea. Now, what's this thing about tune? That sounds like music. We're not talking about music, we're talking about light. And how could a receptor cell be tuned? Well, Young at that time, there's another thing he said in 1801. Light, sound, they both have a lot of properties, they exhibit a lot of properties that are similar to waves on the surface of water. And waves have a frequency. Different waves are distinguished by their frequencies. And there's something about frequency called resonance. If you blow through an organ pipe, it's going to sing. It's going to sing with a musical note with a particular frequency that's got something to do with the dimensions of that pipe, how big it is, low notes from big pipes, and so on and so forth. So, okay, a couple of 100 years go by, and we can illustrate this very beautifully now. Here are some test tubes. Each one's got a suspension of little crystals in it. Those crystals are all exactly the same chemical. They're all cadmium sulfide. They're all exactly the same chemical. It's just that they were allowed to crystallize for different amounts of time. These are all little crystals. These are all big crystals, and there's everything in between. When you put them under black light, they glow in different colors having to do with the physical dimensions of the crystals, which are tuned to separate colors. Now, that's not exactly what we want. That's emitting light. We're talking about detecting light. But I think you know quite well, if you sing to your guitar, you sing a note to your, some of you maybe play guitar, right? You sing a note to your guitar, only one string is likely to respond, the one that's in tune with the note that you're singing at it. At least if you sing better than me. Guitar string only responds to a particular range of frequencies. So Thomas Young says, maybe the spectral color thing is a kind of frequency. Maybe the receptor cells contain something in them that's selective because of some kind of resonance idea. Specifically, let's suppose that receptor is responsive. Let's suppose that the receptor's response to one spectral color is the product of what you get when you multiply the intensity of the light at that color times the sensitivity at that color. It's some linear relationship. That's what some mathematician would say. So let's here are the points that I had already from Young, and here are the new points. We're going to add to these hypotheses that each photoreceptor has a distinct sensitivity range, and they come in only 3 classes. Every photoreceptor cell lies in one of these 3 classes, and everyone in that class is completely identical to every other one in that class, but there's 3 different kinds. Okay, that's Young's hypothesis. What's it got to do with our paradox? Well, here's another kind of spectrum. It's not the same spectrum as before. On this axis, we've still got what kind of color I'm talking about, blue, green, and red. But on this axis, instead of how much light is present, we've got how much light is needed to make that receptor cell respond. Or, put it the other way, it's how sensitive that receptor cell is. So there's 3 different kinds, making 3 different curves. I only drew 2 of them. There's this one that peaks at the green and is especially sensitive to green light. There's this one that peaks in the red, it's especially sensitive to red light. And there's this blue one that we're not going to talk about. If I send spectrally pure yellow light in, it's going to land at the intersection of those 2 curves, and both the green receptor and the red receptor are going to respond equally strongly. If I send in pure green light, then the green receptor is going to respond a lot and the red receptor not very much, and vice versa if I send in red light. But now if I send in a mixture, some of this and some of that in equal amounts, then I'm going to add those 2 responses, and once again, the 2 receptor cells are going to be saying about the same thing. They're going to be responding about equally strong, and I'm going to get the same message going to the brain as if I had sent in spectrally pure light. That's the origin of that ambiguity, says Thomas Young. All the brain can know is what the receptor cells tell it, and since you're testing the light that's coming in with just these 3 sensitivity functions, there's this ambiguity. There's 2 different ways to get the same response. That's Young's great idea. Let me summarize that. There were a lot of ideas there. Pure spectral light has a continuously varying property. I'm going to call that the spectral color. There are all kinds of mixtures possible. You can draw any graph at all, and that corresponds to some kind of light, some kind of mixture. There's billions of different kinds of mixtures you can make, a huge variety of spectra, but our eyes are only sampling those spectra with just 3 sensitivity curves, sending just 3 signals to the brain for every pixel. Each sense depends linearly on the incoming spectrum, and all your brain can know are those 3 signals, and that's why you've got an ambiguity in your color discrimination. It's a loss of some information that's coming into your eyes, but not getting out to your brain. Whoa, way ahead of its time. Remember, the year is 1801. Nobody had ever seen a photoreceptor cell back then, and even when they did, many decades later, when people started to be able to see photoreceptor cells, they all look exactly the same. You don't see any 3 classes. Anatomically, they're indistinguishable. It took 163 years before somebody made the crucial measurement, which I'll tell you about tonight, to confirm Thomas Young's hypothesis. Whoa, good spycraft, I would say. Of course, so great, we're done. We saw something weird in the first part of this talk. We found a hypothesis, seems to explain it, ready to reap those golden rewards, call it the venture capitalists. Whoa. There's a problem with being 163 years ahead of your time, and the problem is peer review. Okay? You can take a lot of flack when you're 163 years ahead of your time. Peer review just wasn't built to handle it. Here's a review that Young got. Difficult to deal with an author, blah, we've searched without success for any trace of learning, acuteness, and ingenuity, blah, blah, blah. A savage review, okay? What are you going to do? Every scientist has had this experience, right? What are you going to do at that moment in your life? Are you going to just crumple up and die? Not necessarily. Now, you know, people who popularize science, they often think they're doing you a favor by collapsing a scientific story down to 2 steps, okay? Let me go through it with you. Step 1, there's Albert Einstein. He's this transcendent genius. He's sitting in a chair. He notices his butt pushing against the chair, and he has this great idea. Step 2, and then we got GPS and lived happily ever after. Well, there are 2 things I don't like about that story, okay? Thing 1, if you're some young person imbibing these stories, after a while you get the point. Oh yeah, I'm not a transcendent genius. I can't play this game. This has got nothing to do with me. Thing 2, if you're a not so young person, a person who pays taxes perhaps, you hear enough of those stories and you start to say, whoa, why does the government support science anyway? Why does it cost so much, you know? There's always going to be 1 or 2 transcendent geniuses on the planet, and throwing a lot more money at it won't make any more than that. And anyway, he had a day job when he had that good idea, you know. And as for the GPS, that's industry. That's what industry does, you know. They make money building stuff. So why do you have to fund science? So the point, of course, is that in between step 1 and step 2, there's this humongous middle step that people leave out. It's called scientific research. And it does cost money, okay? And what I want to tell you about tonight is, one of my texts is what scientific research is really all about. But first, let me answer those 2 hypothetical people. To that young person, I would say, a whole lot of science is actually carpentry. It's actually craftsmanship, okay? There's meticulous patient craftsmanship. You got to build a one-off device or method that's never been built before, that's going to tease out that nugget of information, that's going to advance your spycraft. That's what a lot of science is, and a whole lot of people have those qualities and can do it. Well, to person number 2, I've already said that scientific research does cost money, and in this country, unfortunately, industry has basically stopped doing it, okay? There's a long way to go. Now, well-meaning people, when they tell these stories, you know, they generally think, oh, it would hurt your little brains if I told you about that middle step, or you might be bored for a minute, we can't have that, but that's what I want to do tonight. If I end up demystifying scientists for you, so that you can no longer look at us as mumbo-jumbo voodoo priests, well, that's a good outcome. I'd like that.